In mathematical analysis, a metric space M is called complete, or a Cauchy space, if every Cauchy sequence of points in M has a limit that is also in M, or, alternatively, if every Cauchy sequence in M converges in M. Intuitively, a space is complete if there are no points missing from it, inside or at the boundary. For instance, the set of rational numbers is not complete, because e.g. 2, displaystyle sqrt 2, is missing from it, even though one can construct a Cauchy sequence of rational numbers that converges to it. See the examples below. It is always possible to fill all the holes, leading to the completion of a given space, as explained below. Examples: the space Q of rational numbers, with the standard metric given by the absolute value of the difference, is not complete. Consider for instance the sequence defined by x1 equals 1, displaystyle x underscore 1 equals 1, and xn plus 1 equals xn 2 plus 1 xn, displaystyle x underscore n plus 1 equals frac x underscore n 2 plus frac 1 x underscore n. This is a Cauchy sequence of rational numbers, but it does not converge towards any rational limit. If the sequence did have a limit x, then necessarily x2 equals 2. Yet no rational number has this property. However, considered as a sequence of real numbers, it does converge to the irrational number 2. Displaystyle sqrt 2. The open interval O1, again with the absolute value metric, is not complete either. The sequence defined by xn equals 1, n is Cauchy, but does not have a limit in the given space. However, the closed interval O1 is complete. For example, the given sequence does have a limit in this interval and the limit is 0. The space R of real numbers and the space C of complex numbers, with the metric given by the absolute value, are complete, and so is Euclidean space Rn, with the usual distance metric. In contrast, infinite-dimensional normed vector spaces may or may not be complete. Those that are complete are Banach spaces. The space C, A, B, of continuous real-valued functions on a closed and bounded interval is a Banach space, and so a complete metric space, with respect to the supremum norm. However, the supremum norm does not give a norm on the space C, A, B, of continuous functions on A, B, for it may contain unbounded functions. Instead, with the topology of compact convergence, C, A, B, can be given the structure of a fresh A space, a locally convex topological vector space whose topology can be induced by a complete translation invariant metric. The space QP of p-adic numbers is complete for any prime number p. This space completes Q with a p-adic metric in the same way that R completes Q with a usual metric. If S is an arbitrary set, then the set Sn of all sequences in S becomes a complete metric space if we define the distance between the sequences xn and un to be 1, n, where n is the smallest index for which xn is distinct from un, or 0 if there is no such index. This space is homeomorphic to the product of a countable number of copies of the discrete space S. Some theorems. A metric space X is complete if and only if every decreasing sequence of non-empty closed subsets of X, with diameters tending to 0, has a non-empty intersection. If Fn is closed and non-empty, Fn plus 1 Fn for every n, and diam Fn 0, then there is a point X element of X common to all sets Fn. Every compact metric space is complete. though complete spaces need not be compact. In fact, a metric space is compact if and only if it is complete and totally bounded. This is a generalization of the Heine-Borel theorem, which states that any closed and bounded subspace S of Rn is compact and therefore complete. Let X, D, X, Y be a complete metric space. If AX is a closed set, then A is also complete. Let X, D, X, Y be a complete metric space. If AX is a complete set, then A is also closed. If X is a set and M is a complete metric space, then the set B, X, M, of all bounded functions f from X to M is a complete metric space. Here we define the distance in B, X, M, in terms of the distance in M with a supremum norm, D, F, G, sup, opening curly bracket, D, F, X, G, X, X, element of, X, closing curly bracket, display style D, F, G, equivalent, sup, left D, F, X, G, X, X in X, right. If X is a topological space and M is a complete metric space, then the set C-flat, X, M, consisting of all continuous bounded functions f from X to M is a closed subspace of B, X, M, and hence also complete. The Baire category theorem says that every complete metric space is a Baire space. That is, the union of countably many nowhere dense subsets of the space has empty interior. The Banach fixed point theorem states that a contraction mapping on a complete metric space admits a fixed point. The fixed point theorem is often used to prove the inverse function theorem on complete metric spaces such as Banach spaces. The expansion constant of a metric space is the infimum of all constants. Mu, display style, script style, mu, such that whenever the family, opening curly bracket, B, X, alpha, R, alpha, closing curly bracket, display style, script style, left over line, B, X underscore, alpha, backslash, R underscore, alpha, right, intersects pairwise, the intersection, alpha, B, X, alpha, mu, R, alpha, display style, big cap underscore, alpha, over line, B, X underscore, alpha, mu R underscore, alpha, closing curly bracket, is non-empty. A metric space is complete if and only if its expansion constant is 2. Completion. For any metric space M, one can construct a complete metric space M, which is also denoted as M, which contains M as a dense subspace. It has the following universal property. If N is any complete metric space and F is any uniformly continuous function from M to N, then there exists a unique uniformly continuous function f from M to N, which extends F. The space M is determined up to isometry by this property, and is called the completion of M. The completion of M can be constructed as a set of equivalence classes of Cauchy sequences in M. For any two Cauchy sequences x equals xn, and y equals un, in M, we may define their distance as d, x, y, equals lim, n, d, x, n, y, n, display style d, x, y, equals lim underscore n, d, left, x underscore n, y underscore n, right, closing curly bracket. This limit exists because the real numbers are complete. This is only a pseudometric, not yet a metric, since two different Cauchy sequences may have the distance 0. But, having distance 0, is an equivalence relation on the set of all Cauchy sequences. And the set of equivalence classes is a metric space. The completion of M The original space is embedded in this space via the identification of an element X of M with the equivalence class of sequences converging to X, i.e., the equivalence class containing the sequence with constant value X. This defines an isometry onto a dense subspace, as required. Notice, however, that this construction makes explicit use of the completeness of the real numbers. So completion of the rational numbers needs a slightly different treatment. Cantor's construction of the real numbers is similar to the above construction. The real numbers are the completion of the rational numbers using the ordinary absolute value to measure distances. The additional subtlety to contend with is that it is not logically permissible to use the completeness of the real numbers in their own construction. Nevertheless, equivalence classes of Cauchy sequences are defined as above, and the set of equivalence classes is easily shown to be a field that has the rational numbers as a subfield. This field is complete, admits a natural total ordering, and is the unique totally ordered complete field. Up to isomorphism, it is defined as the field of real numbers. See also construction of the real numbers for more details. One way to visualize this identification with the real numbers as usually viewed is that the equivalence class consisting of those Cauchy sequences of rational numbers that ought to have a given real limit is identified with that real number. The truncations of the decimal expansion give just one choice of Cauchy sequence in the relevant equivalence class. For a prime p, the p-adic numbers arise by completing the rational numbers with respect to a different metric. If the earlier completion procedure is applied to a normed vector space, the result is a Banach space containing the original space as a dense subspace. And if it is applied to an inner product space, the result is a Hilbert space containing the original space as a dense subspace. Topologically complete spaces. Note that completeness is a property of the metric and not of the topology, meaning that a complete metric space can be homeomorphic to a non-complete one. An example is given by the real numbers, which are complete but homeomorphic to the open interval, or one, which is not complete. In topology, one considers completely metrizable spaces. Spaces for which there exists at least one complete metric inducing the given topology. Completely metrizable spaces can be characterized as those spaces that can be written as an intersection of countably many open subsets of some complete metric space. Since the conclusion of the Baire category theorem is purely topological, it applies to these spaces as well. Completely metrizable spaces are often called topologically complete. However, the latter term is somewhat arbitrary since metric is not the most general structure on a topological space for which one can talk about completeness. See the section Alternatives and Generalizations. Indeed, some authors use the term topologically complete for a wider class of topological spaces. The completely uniformizable spaces. A topological space homeomorphic to a separable complete metric space is called a Polish space. Alternatives and generalizations. Since Cauchy sequences can also be defined in general topological groups, an alternative to relying on a metric structure for defining completeness and constructing the completion of a space is to use a group structure. This is most often seen in the context of topological vector spaces, but requires only the existence of a continuous subtraction operation. In this setting, the distance between 2 points x and y is gauged not by a real number e epsilon via the metric d in the comparison d, x, y, less than epsilon, but by an open neighborhood n of 0 via subtraction in the comparison x minus y element of n. A common generalization of these definitions can be found in the context of a uniform space. where an entourage is a set of all pairs of points that are at no more than a particular distance from each other. It is also possible to replace Cauchy sequences in the definition of completeness by Cauchy nets or Cauchy filters. If every Cauchy net, or equivalently every Cauchy filter, has a limit in X, then X is called complete. One can furthermore construct a completion for an arbitrary uniform space similar to the completion of metric spaces. The most general situation in which Cauchy nets apply is Cauchy spaces. These two have a notion of completeness and completion just like uniform spaces. See also Naster-Tarski theorem. Completion. Algebra. Notes. Kelly, John L. 1975. General Topology. Springer. ISBN 0-387-90125-6. Kreyszig, Erwin. Introductory Functional Analysis with Applications. Wiley, New York, 1978. ISBN 0-471-03729-X. Lang, Serge. Real and Functional Analysis. ISBN 0-387-94001-4. Mies, Reinhold, Vogt, Dietmar. 1997. Introduction to Functional Analysis. Ramanujan, M. S. Trans. Oxford, Clarendon Press. New York, Oxford University Press. ISBN 0-19-851485-9.